Hi, hello everyone. Welcome back to Deep Learning video lecture series. And this is Dr. Chiranjeevi Manike, Professor in Data Science and Cybersecurity Department, MLR Institute of Technology, Hyderabad. So in this lecture, I'm going to explain the simple code, that is how we can implement a single layer and a multi-layer perceptron. And I will also show and what libraries we need to import. Like suppose if you want mainly the multi-layer perceptron, implement using this TensorFlow, the PyTorch, what are the libraries need to be imported. So this is very simple. That is mainly our objective is to understand the fundamental programming like multi-layer perceptron and the single layer perceptrons. But single layer perceptron is only to understand, but the multi-layer perceptron, because in the real world, so there will be many number of neurons and hidden layers and output layers, because the single layer will have only one input layer, and output layer, whereas a multi-layer perceptron would have many number of like input layer, output layer, and also the hidden layers. So let us quickly understand, and this is the code. So let us first connect so that we can execute each line in interactive mode. That is, you can also execute this Python code in a batch mode also. But I kept this entire code in a cell so that it would be executed in batch mode. So first let us try to understand the each line quickly, so that you can also implement, mainly like who want to develop deep learning models, who want to work on deep learning like image processing, natural language processing, if you want any develop any AI applications, so they must understand the concept, that is a theoretical aspect, and also the programming point of view. So previous lecture, I have already explained what are the fundamental Python libraries you need to explore, and also the deep learning libraries like TensorFlow and PyTorch. So let us connect, because I am executing this code in Google Colab. So we have to connect to the cluster. So it will take little time initializing. So it is connected. So now let us see here the first line, import numpy, because this is a implementation of a single layer perceptron. So we are not going to import any other like libraries from the PyTorch or TensorFlow. So here we use basic libraries of Python like NumPy, etc., to implement this single layer perceptron. This is only for understanding purpose. So here, this is the way we can import NumPy as a NP. Next we can generate the sample data set, that is to mimic how we can implement this XOR gate function using the single layer perceptron. So we have to generate the input. Input is a two-dimensional vector, like here you can see, because if you take two inputs x1 and x2, and this each value, right, this each represents one row, and this is the next row and next row, like this. That means 0, x1 0, x2 0, and x1 0, like that. And the corresponding output, that is y, and that is also created as a numpy array, that is np.array of. So here the output, like for this 0 0, if input x1 and x2 both are 0, and then the corresponding output of this XOR function is 0. And here this is for this input 0 1, and the corresponding output of this XOR function. Next, similarly, like 1 0 1 1, and the corresponding outputs. Sorry, it's a logical AND gate output. So next thing is we have to initialize the weights and biases. These are only the tunable parameters. So how do we initialize this? So here we can use this again, the numpy's random function here, the random, that is to generate the random values. You can see here, if you place the cursor and it will display the information about the function here. And this is to create a generator, that is, and it's called methods. So this is a non-random number distribution, that is a default range, and this is the size of this matrix that is need to be generated. Okay, so 2 by 1 because two weights, so and it should be 2 by 1 matrix. Next, bias only we need because of only one neuron, so we can create only one value. It's a one dimension, so single dimension. It's a vector. Let's say it's a scalar value. Next, learning rate, we are giving like 0.1 as learning rate, very small learning rate, and the number of epochs are initialized to 100. So next, activation function. So we need activation function, like we discussed many different types of activation functions, and also the popular activation functions like ReLU, sigmoid, softmax, etc. So, and here this is the way we can just define a simple step function in this singular perceptron. So this is the way we can define the function in Python. So it takes this is a parameter, it has one parameter, and it is going to return, and this is a function, right? Here you can see here it's a function. It returns where the condition and the x and y, and that is based on the condition it evaluates. That means it is going to select the value. Like for example, if the condition, that means x value is greater than or equal to 0, then it will print 1. If else, it prints 0. So that is how this function, step function, works. Means it produces either 0 or 1. So basic step function. Next, we can create this training loop. So because we have to train the model. So for example, here the number of epochs, and the epoch, it's a variable, right? So it takes the values, that is range from the beginning, like starting value to the number of epochs. So, and the linear output, and this is a variable. And now here you can see here the first dot product, that is weighted sum of a weighted sum, and then we'll add the bias. So here np dot and this is to produce the dot product of these two matrices x and weights, and then the bias term bias will be added. Next, y predict, this is a predicted value. So the step function returns, like if you supply this linear output to this step function, it returns a output either 0 or 1, and that will be stored in this y underscore predict variable. Then we have to compute the error. So how do we compute the error? So by finding the difference between the actual value, that is y here, and then predicted value, y underscore predict, and that would be calculated as a error. Next, we have to update weights and biases using the perceptron learning rule. How we can update the weight and biases? Like as we already discussed, so weight would be updated, that is equal to learning rate times np dot product of x transpose and the error, and this the result of the dot product of these two, and then multiplied with the learning rate. Next, similarly, the bias also would be updated, that is learning rate times np dot sum of error. So then here, that is when we need to update the parameters like weight and bias, so that we can decide, like suppose here after 10 epochs, so bias and weights would be updated. So that would be controlled by using this if condition. If epoch and percentage mod, that is 10 equal to 0. So that means for 10 and 20 and 30, 40, 50, 60, like that, for every 10 iterations, the weights and biases would be updated. So the loss equal to np dot mean, and we can calculate this np square root of error. and then we print this, and this is F stands for to print the format in this format in epoch, and the loss would be printed. Next, and we are going to predict, like, and this is just an output that is to display the final predictions. And this print, that here we are going to invoke the function step function. So then np dot product of x and weights and then biases. So this is the output. So let us run this code here. You can see here. Okay, and these are the, and this is the output printed because of these two, right? The final predictions here. And the epoch and loss we have already, this is the printf statement. So here we have printed this epoch and loss. Like you can see, the every 10 iterations we have calculated, and then the final predictions are printed like 0 1 0 1. Let me run it again. So there's no loss because it's a very simple function, right? It's very just only for understanding. So that's about a single layer perceptron implementation. This is only for understanding, that is to the beginners. Next one is implementing the multi-layer perceptron. In this, I'm going to explain the code related, like how we can implement this multi-layer perceptron using a TensorFlow as well as a PyTorch. As we already discussed the differences between the TensorFlow and PyTorch. So TensorFlow mostly used in a development, whereas PyTorch is more user-friendly. And we already discussed the features of this, mainly the differences between these two, and you please go to the lecture. So now I'm going to explain how we can implement this multi-layer perceptron using TensorFlow. So here you can see, because some fundamental operations need to be done, so that we have to rely on the fundamental package of Python like NumPy, Pandas, and Matplotlib, that is for visualization. And so here I have imported this NumPy as NP, and then you can see here from TensorFlow.keras.models we have imported sequential, and then TensorFlow.keras layers we have imported the dense. So our network is going to, this multi-layer perceptron network is going to have the two layers. One is input layer and another output layer. So you can see, you will understand also. So I'll explain with the numerical example also for this same model. So now let us generate this the sample data. That is, this is a sample data and the corresponding XOR problem. The similar like how we like in a single layer perceptron. Next, build the multi-layer perceptron model. So the model need to be built. So first we define the model, that is a sequential model. So model equal to sequential, that is to stack the layers, stack the layer one to another. That means one layer output will be the input of the next layer, and then that layer output will be the input of the next and subsequent layers. So this is the way we can stack the layers in sequential manner. So then, and the input layer would be defined like here you can see here, model.add and dense layer. So dense means I have already explained like dense and sparse. So here, and it is going to have 4 neurons. This input layer is going to have 4 neurons, and the input dimensions are 2, means it is going to expect the two features, and in this we are going to use activation function as a ReLU, rectified linear unit. Next, the output layer, that is we can add this output layer, that is model.add, so dense, and this is going to have only one output. So then the activation function, you can see here, the sigmoid activation function. So next we can compile the model, that is by using this model.compile. So once you define the model, then you would access the attributes, like this is the compile, and we have to pass the arguments for the parameters like optimizer and we are going to use the Adam that we already discussed, like different optimizations. Next, loss function that we are going to use is a binary cross entropy that I will explain now. And then metrics we are going to use is accuracy. So then train the model. So here the model dot fit, and this is the input and this is the output, and the number of epochs are initialized to 100, and this we will discuss it later. Next, prediction. So here the model dot predict of 0.5 and the type, and this is going to produce, that is it is going to predict, and then we'll print the results, that is the final predictions, that is predictions. So now let us run this code. Before we have to install this. If you have not yet installed TensorFlow, we have to install, that is by pip install TensorFlow. So if you run this code, and it will get installed. So let me clear this output. Yeah, so next one is, so we are going to run this part in batch mode. That means the lines, the set of lines, not I'm executing line by line, I'm executing the all lines or set of lines at a time, the code. So that is the difference between the interactive and the batch mode of running the code. So here you can see the final predictions, 1 1 0 1. Next, another, I think before let me finish this part also, like implementation of multi-layer perceptron using PyTorch. This is another framework we have. So here, what are the libraries we need to import? Import a torch, and this is a multi-layer perceptron implementation using the PyTorch. So next, a torch neural network as a neural network, and torch.optimum, optimum as optimum, and generate the sample data, and this is same, and define the multi-layer perceptron. Here, this is the way we can define the model, multi-layer perceptron model, and the super. This I think because initially we'll focus on the TensorFlow, so we will discuss all these terms and etc. right in coming lectures. So multi-layer perceptron and self.hidden layer, and this is the way 2 by 4, that means 2 inputs and 4 neurons input layer. This is a hidden layer. Next, self.output, that is neural network linear, that is 4 1, that is 4 neurons, and hidden layer output layer is 4 to 1. Next, forward pass, that is we have to pass this weighted sum to the ReLU activation function, that is for hidden layer, like by using x equal to torch.ReLU, and self.hidden of x would be passed to this ReLU activation function. Next, this is the another, right, whatever the value that is received from the hidden layer, and that will be passed to the output layer, where the output layer have the sigmoid activation function as a sigmoid. So then return x. So instantiate the model, that this is the way we can instantiate the model equal to MLP, and loss and optimizer. So here binary cross entropy loss we have used in this implementation multi-layer perceptron, both in TensorFlow and PyTorch. So here we are going to use the Adam optimizer, and then the training loop, like 1000 epochs. We have set this number of iterations 1000, and here it will be executed. So optimizer dot 0 underscore grad, that is to clear the gradients, and output equal to model of x, that is forward pass, and the loss would be calculated, that is criteria of outputs, and that is to compute the loss function. Next, loss backward, that is the back, we need to propagate back to adjust the weights and biases. So the backward pass, that is loss dot backward, and optimizer step, that is to update the weights. So then here again, when we need to update the weights, that would be controlled by using this condition here. Next, prediction, and this is the final predictions we will be So we'll pass the value and then we'll check the predictions. So this is, let me run this code it again. So this is right, very simple, and it is taking a little bit more time, so that if you want to work on like images, any other deep learning, complex deep learning models, and you have to rely on the cloud. You have to purchase or you have to make use of the cloud services to run your deep learning models. Okay, so this is the output that is produced by the multi-layer perceptron simple using the PyTorch. So final predictions. So now let us, like, because here in this we have used binary cross entropy loss function. So let us see what is this binary cross loss entropy function. Okay, so what is a binary cross entropy? It's a binary cross entropy, BC, is a loss function mainly used for the binary classification problems. That means where the target labels are either 0 or 1. So it mainly measures the difference between the true label and the predicted probabilities from a model. Like, that is only based on that we will measure the loss. So let us see the equation, mathematical part, that is the loss, and this is the equation we use to calculate this binary cross entropy. Let us see what are the terms in this equation, where L is a loss, that is a binary cross entropy loss, and here n is the number of samples in a data set we are going to use for the binary classification, and then yi is the true label for the ith sample. Because it's a binary classification, the output is, the target label is either 0 or 1. So that's why the sample, like true label for the ith sample, is either 0 or 1. So next, y hat, that is a predicted probability for the ith sample, that is a predicted one, and this is the true label. So we have to find out the difference. So why we use this logarithm here, like, so if you go through this equation, so we use log of y I hat and log of y minus y hat. Why we use this? So because, let us understand why. So the log function mainly ensures that the small errors are penalized less and the large errors are penalized more. So it smooths the gradients for better optimization during the back propagation. That is a main reason. So when to use the binary cross entropy, or when we should avoid this usage of this binary cross entropy. So we use the binary cross entropy when the problem is a binary classification. That means the target label is either 0 or 1. So the model outputs a probability that is between 0 and 1. Example, using the sigmoid activation function. And when we do not use this BC, binary class entropy, so the binary class entropy problem is like, if the problem is a multi-class classification, that means we cannot use this binary class cross entropy. So in that case, we have to use this the categorical cross entropy instead of this BC, binary cross entropy. So the model outputs raw score, that is instead of probabilities. So thank you for watching.